Recording. Okay, cool. And then I'll go ahead and share my screen. But yeah, so I guess you all already know me. I'm Natalie, I'm your TA. If you haven't had a chance to visit my office hours, please do. Those are on Mondays at 10 a.m. And so I'm currently a second year PhD student in biomedical engineering here at USC in Professor Megan McCain's Laboratory for Living Systems Engineering. And today I'll be giving a guest lecture on photolithography, microcontact printing, and microfluidics. And so these are technologies, microfabrication techniques and technologies that we use regularly in our lab, in our research, and that are kind of more broadly used by the field of tissue engineering. So as a brief outline of the course today, we'll be describing two microfabrication techniques called photolithography and soft lithography. This will take up sort of the first half of lecture. And then in the second half, we'll describe their applications in tissue engineering, specifically microcontact printing and microfluidic devices. And then lastly, we'll go through some research examples of these. And if at any point you all have questions, please don't hesitate to just unmute yourselves and interrupt me at any point during the lecture. But before we jump into these microfabrication techniques, I wanted to begin with sort of an overview of why we're interested in these microfabrication techniques in the first place. So far in this course, you've learned about a lot of different cell sources and also various biomaterials, both natural and synthetic. And so today we'll be describing microfabrication techniques that allow us to combine cells and biomaterials in such a way that we start to mimic features of tissues in the body. And so the first technique that allows us to do this is called microcontact printing. This is pictured here in this flow chart. This is essentially like rubber ink stamping, but instead of stamping ink, we're transferring cell adhesion proteins into desired patterns. And when we culture cells on these patterns, they'll kind of preferentially adhere to these cell adhesion proteins. And patterning cells in such a way allows us to mimic the structure of tissues in the body. So in the example on the right here, we have an image of cardiac tissue in the body. So you can see that the cardiomyocytes, or the heart muscle cells in pink here, are very much aligned with one another in the body. And this allows them to contract all in the same direction for optimal force generation. And we can mimic this structure in vitro through engineered cardiac tissues by using this process of microcontact printing to print sort of lanes of cell adhesion proteins that guide the cells to align with one another in a similar way, in a similar structure as they do in the native tissues in the body. And sort of a second technique that we'll be describing today is microfluidic devices. So we're starting with a similar substrate, so a biomaterial with features at the scale of cells, with microscale features. But instead of using this to stamp proteins as we did in microcontact printing, we're going to bond this to another substrate, such as glass, and create microchannels in which we can seed cells and expose them to fluid flow. And this is called a microfluidic device. And on the right here, we have an application of microfluidics in tissue engineering. So this microfluidic device has 4 channels, a top channel, a lower channel, and 2 lateral channels. And you can see that we can start to compartmentalize cell types. So there are human intestinal epithelial cells, so gut cells, in the top channel. There are vascular cells lining the lower channel and immune cells flowing through the media or blood. And then we have 2 lateral channels, which we can connect to a vacuum to start to introduce even mechanical features of the environment, such as strain. So the common feature between microcontact printing and microfluidic devices is that the commonality here is that we're starting with a similar PDMS substrate that has features on the scale of cells, or microscale features. So how do we actually make a biomaterial with features that small? So that is where our two microfabrication techniques come in. These are called photolithography and soft lithography. And they're essentially techniques to make PDMS stamps for microcontact printing or microfluidic devices. And so this is a visual outline of everything we're going to cover today in lecture. So you don't actually have to understand everything on this slide just yet, but we'll keep referring back to this throughout the lecture. So hopefully this makes more sense by the end of lecture. But we'll start by describing photolithography. So in photolithography, we're going to use UV light to selectively expose regions of a material, a light-sensitive material, to light, in order to kind of selectively create these microscale features in regions that we want them to be in. And so we'll go through the process of this now. But before we begin, because we're working with really small features on the scale of microns, dust is actually around 1 to 100 microns in size. And so we'll need to work in a really clean environment, which is called a clean room. And so ambient air actually contains 35 million particulates in every cubic meter. And so we'll need to work in a class 100 clean room, which filters this down to 3,500 particles per cubic meter. And so we have a class 100 clean room here on campus. This is actually located, it was previously located in Vivian Hall, but it's getting relocated currently to the basement of Michelson. For even smaller features, so if we're working with features on the nanometer scale, such as the integrated circuits in computing devices, you'll need to actually work in a class 10 clean room, which has even less, so 350 particles per every cubic meter. And so Intel campus, for example, has several class 10 clean rooms. Okay, so how does a clean room work? So essentially you're just filtering out particulates from ambient air using a series of HEPA filters, which we've talked about in our biosafety cabinet cell culture lecture. So this is basically just filtering out particles by size. And once air actually enters this clean room, there's also airflow directed towards the ground and towards these exit vents. And this sort of just minimizes the amount of dust and particles that are freely floating in the air while you're performing your experiments. And then as you can see in this figure, humans bring with them lots of dust, like dead skin cells and stuff like that. And so humans actually have to wear what's called a bunny suit, which is pictured here, which is covering essentially all of your skin. And you also have goggles here, as you can see, to cover your eyes and everything. And so sort of this last feature of a clean room is this yellowish hue. So we're working with light sensitive materials, materials that are specifically sensitive to UV light. And regular fluorescent lamps actually do emit some light on the UV spectrum. And so these have to be filtered out. So we're filtering out lower wavelength light and we're left with this sort of unpleasant yellowish color. Okay, so now that we're in the clean room, we can start to describe this process of photolithography. So photolithography means that we are using light. If you break it down into its Greek roots, it means that we are using photo, light, to write into stone. So what is the stone that we are using? It consists of two things, silicon wafers and photoresist. So silicon wafers are made up of the element silicon, which is the second most abundant element in the Earth's crust. So here's a picture of sand, and sand is silicon dioxide, which is also called silica. But as you could imagine, it's very abundant on the Earth's crust. And so silicon wafers are just very purified silicon that's been melted down and then cooled, and then sliced into these wafers, which are very crystalline and brittle. And so these are roughly the thickness of like a CD or DVD, and their diameters range between 1 and 12 inches, depending on your application. And this provides us with sort of a clean slate for the photolithography process. And on the right here, because silicon itself is not light sensitive, we'll need to coat it with a light sensitive material. And this is called photoresist. And so here is sort of the setup for photolithography. So we're going to selectively expose this photoresist that's on top of our silicon wafer to UV light through a mask. So this mask contains opaque regions, which are shown in black here, that block light, and transparent regions in white here that enable light to hit the photoresist below it. And then either one of two things will happen. If you're working with negative photoresist, those exposed regions, so anything under the transparent regions, will become cross-linked such that they are insoluble. And then those unexposed regions that were below the opaque regions can be washed away. And your pattern that you are left with is sort of the opposite of that opaque pattern that you started with on your mask. If you're working with positive photoresist, the opposite is true. So exposed regions will sort of get degraded or can be soluble and washed away, whereas unexposed regions will remain on your wafer. And so the way that I like to remember this is by thinking about positive and negative numbers. So if your mask refers to the number 1, negative photoresist will give you the inverse of that mask, or a -1. And positive photoresist will give you back the sort of exact replica of your mask. Okay, so I hope you all are listening because I do have a poll question on this. So before I read this out, I just want to point out that I have a different username than Nathan, or than Dr. Cho, sorry. So my username is Natalie Khali, Khali 241. So I'll give you like maybe 15 seconds to enter that, or maybe 30 seconds, and then I'll read out the question. Okay, I see I'm starting to get some results, so I'm just going to read out the question. Suppose you perform photolithography with the mask below. The transparent regions, which are in white on this mask, which received light, become cross-linked to form the pattern below. Did you use negative or positive photoresist? All right, looks like we're at 20 responses, so I'll give it some more time to get the rest of you. It looks like we're kind of stuck at 23, 24 responses. If you don't know, maybe just guess and we'll discuss the answer together in a few seconds. All right. And also, if anyone has any questions, you can just unmute yourselves and ask now, or anytime throughout the lecture. Okay, yeah, so the majority of you said negative photoresist, which is the correct answer. So we discussed how negative photoresist becomes cross-linked or insoluble when exposed to light. So those sort of white regions in the mask will become patterns on the wafer. So we'll end up with the inverse of the mask. And again, just an easy way to remember this is to just assign them numbers. So if your mask is the number 1, with negative photoresist, your pattern is the inverse of that. You'll get a -1. Okay, and so one of the pieces of equipment that you'll need for photolithography is a mask. So this contains your sort of custom designed features that you want to use either for cell patterning or microfluidic devices, etc. And so this pattern is designed in a CAD program and then printed onto either a polyester transparency if you have features that are 10 microns or larger. And this is sort of a flimsy and also cheaper alternative. Or you can also use a chrome mask in which chrome is directly printed onto a piece of glass, which is pictured below here, using a technique called electron beam lithography. This is a lot higher resolution. So if you have features that are 1 microns or larger, but more expensive. And then once you have your mask, the first step of photolithography in the clean room is wafer spin coating. So in this step, your silicon wafers are spin coated with photoresist to create a thin and even layer of photoresist on the wafer. As we described, wafers themselves are not light sensitive, so this step is necessary. And so this is what a spin coater looks like. It's essentially got this circular region, which if we look at it from the side, looks like this. You'll place your wafer on that chuck, and it also has a hole that leads to a vacuum pump in which suction is applied to hold the wafer in place. And then this will just spin at very high spin speeds to sort of bring all of the photoresist towards the perimeter of the chuck or the wafer, and you'll be left with a really even layer of photoresist. And so photoresist, so I've worked with it in the lab, it's very viscous, and it actually comes in many different, there are many different types of photoresist that range from 1 to 300 microns in thickness, depending on the application. And the thickness of your photoresist will determine the thickness of your features. And so because we're working with something that starts out sort of viscous, the next step is to actually evaporate out some of the solvent in order to be left with a dry layer of photoresist, something that is more like solid. And so that's what's shown here. So you'll place your wafer with photoresist on a hot plate. This is called a soft bake. That's the name of this step. And this just evaporates out some of the solvent in order to dry the layer of photoresist. Okay, so once you have an even layer of photoresist on your silicon wafer, the next step is to align the wafer with the mask using what's called a mask aligner. This is pictured here. But essentially, if your wafer is sort of tilted in relation to your mask, this is bad because as we can see in this, this image of the fork here, light has this property where it will bend around corners. And this is called diffraction. And so in this example, a light source is sort of hitting a fork and bending around the edges of this figure such that its projection onto the surface below it is sort of blurry. And so we want to minimize this by bringing the photoresist and the wafer as close as possible to our mask such that we're making contact and that it's level with the mask. And so we do this using a machine called a mask aligner, which is pictured here. We actually have this exact model at USC. And so you'll place your sample, your silicon wafer, on the sample holder, and then you'll sort of push it beneath this central region where above this, there's another stage that you can place your mask on. And then using some of these knobs, so these two and then one that's kind of hidden here, you can adjust the X, Y, and Z directions until your wafer is aligned with your mask. And then another feature of this mask aligner is it contains this lamp house, which contains the UV light source. And one of these buttons, this blue one here, actually says expose. And so once your mask is aligned with your wafer, you'll expose it to UV light through the mask aligner. And so in the case of negative photoresist, this process is going to cross-link exposed regions of the photoresist. And so once you place the wafer with photoresist on a hot plate, this is your last step. This is like your, it's called a post-bake. This is where a lot of the cross-linking will actually happen, where those exposed regions will become insoluble. And then any of those unexposed regions are left soluble and can be washed away. And so this is called wafer developing. So to actually wash away those unexposed regions, the wafer is then immersed in a developer solution, which is pictured here, such that those unexposed regions will dissolve away, and you'll be left with just your exposed regions on the wafer as physical features. Okay, and here's an example of what that looks like. So this is a silicon wafer with tons of small features on its surface. Okay, so now I sort of have a series of poll questions. We've concluded the part of the lecture on photolithography. So the first question is to select the option that lists the steps of photolithography in the correct order. So we talked about all of these various steps, including the soft bake, UV exposure, alignment, post-bake, spin coating, and development. So now please take a moment to just select which one you think has all of these steps listed in the correct order. Okay, I'll give it a few more seconds because on the last question we received 25 responses. So let's see if three more of you can respond to this poll before we move on to the answer. Does anyone have any questions at this point while we're waiting? Sounds good. You guys are a smart class, so I didn't expect you to have too many questions. All right. Yeah, so we have spin coat, soft bake, mask alignment, UV exposure, post bake, and then development. That is the correct answer. So let's see, what was the other option? Spin coat, mask alignment, UV exposure. Yeah, so the soft bake and post bake steps were out of order in that question. Otherwise, the rest were correct. So the soft bake step actually happens immediately after you spin coat the photoresist. That is because, as I've mentioned, the photoresist is initially dissolved in a solvent. And so after we spin coat it, we need to evaporate out some of that solvent so that we're left with just the photoresist in a dry layer. Okay, so here's another poll question. This one's more visual. Sorry, the other one had so many words on it. But in this case, we have an image that you saw on a previous slide of the process of exposure through the mask at the photoresist. And so the question is to name the substrate in the image below. So that gray box. Is that the mask, the photoresist, the silicon wafer, or polystyrene? All right, let's see what the majority of you selected. Silicon wafer, correct. So the photoresist, which some of you did select, is that red layer, so the arrow above the substrate, because that's the one that needs to be sort of directly exposed to the UV light source. It's not polystyrene because we didn't talk about polystyrene in this lecture, but that's what makes up like cell culture dishes, like Petri dishes, for example, but that's not used in photolithography. Okay, so that was photolithography. We learned how we can make features that are that small at the scale of cells. So now we'll talk about replicating those features in a biomaterial. And that process is called soft lithography. So the biomaterial we'll be working with is called PDMS. You learned about this in a previous lecture, but PDMS has many desirable properties that makes it a commonly used biomaterial. This includes that it's transparent, it's biocompatible, it's also gas permeable, so oxygen can reach cells that are cultured on PDMS. So for all of these reasons, we're going to be working with PDMS. It is going to be poured onto the wafer. So here we have a wafer with microscale features. We'll cast PDMS around these features. And remember, PDMS, the prepolymer solution is a liquid, but after we add the cross-linking agent and bring it to a higher temperature, this process is called curing, it will become a solid, at which point we can peel it off of the wafer. And those features will be replicated, the inverse of those features will be replicated in our PDMS. And so this is shown in sort of real practice on the right here. So PDMS is poured onto the wafer in A, cured, and then peeled off of the wafer. And in this example, you can see that when we're looking in C just at the PDMS replica, you can see that light is refracting off of these tiny features that are on the surface of the PDMS. So the features have been transferred to PDMS here. And then in D, we're just cutting out these 8 different stamps for use in the next process, the next part of lecture, which is called microcontact printing. So we kind of touched on this at the beginning of lecture. It's essentially like rubber ink stamping. So we'll transfer that piece of PDMS with microscale features that has been coated with a cell adhesion protein to a glass cover slip, a PDMS coated glass cover slip. And this will transfer those patterns onto that PDMS coated cover slip. And then cells can be seeded and guided to adhere to those pattern regions. So we talked about how we make this stamp. The next step will be to talk about how to make this PDMS coated glass cover slip. So PDMS is spin coated onto glass cover slips in a very similar method that we spin coated photoresist onto silicon wafers for photolithography. And so we're left with an even layer of PDMS that can then be cured. And then because we talked about how PDMS is very hydrophobic to the point that when proteins absorb onto its surface, they'll actually denature. And so to address this, these cover slips will also be treated with plasma or UV, which was also described in previous lectures. And this oxidizes the surface. It makes it more hydrophilic and promotes absorption of ECM proteins onto its surface. And so here's just sort of a schematic of what we're doing. So we start with a very hydrophobic surface of PDMS, so we can see the high contact angle and all of these hydrophobic methyl groups. After surface activation through UV or plasma, we've replaced some of these methyls with hydroxyl groups and then can absorb proteins onto the surface. And so this is the process of microcontact printing, but sort of up close. So in this case, we start with rectangular lanes. We coat this PDMS stamp with cell adhesion proteins. In this case, we're working with fibronectin. And then we use compressed air to remove any excess fibronectin solution. So we're just blowing off the excess solution. And then we invert this stamp onto our cover slip, which has been activated through UV or oxygen plasma. And then when we remove the stamp, sort of immediately, these proteins will transfer onto the surface of our PDMS coated cover slip. And then we can seed cells of interest. In this case, we're working with cardiomyocytes from rats. And those cells will then adhere to the patterned proteins. So in practice, these cells can actually sort of migrate off of these regions. And so we need to actually add something to block the non-patterned regions, to block cells from adhering to the non-patterned regions. And so that material that we're going to add is called pluronic F127. This is a surfactant, which just refers to a material that has both hydrophilic and hydrophobic regions. So in the case of pluronic F127, this is a tri-block copolymer, which means it contains 3 blocks or 3 polymer blocks of polyethylene oxide and polypropylene oxide, so PEO and PPO. And the center here, the polypropylene oxide, is hydrophobic and will actually absorb onto the PDMS surface. And the tails, the ends, the PEO blocks, are hydrophilic, and so they'll lift off into solution. And this will actually sort of through steric hindrance physically block cells from migrating off of the patterned regions and onto the remainder of the PDMS surface. And so in the figure on the left here, you can see in red, extracellular matrix proteins are patterned onto this cover slip, and cells are sort of shown in black here. And then if we look at these under white light, you can see that cells, there's sort of an invisible barrier here, where cells are not migrating off of this pattern, and that's because it has been blocked with pluronic. Okay, so what are the applications of microcontact printing? Why are we interested in doing this? So we talked about sort of at the beginning of lecture, this application of tissue engineering, or mimicking features such as alignment of cardiac muscle. But we can also control single cell shapes. So this is called cell engineering. So on the left here, cardiomyocytes were seated onto squares where the height was equal to the width. So this is a 1-to-1 aspect ratio pattern. And you can see on the left we have actin, and on the right we have the sarcomeres. The sarcomeres are not very aligned when the cells are seated onto 1-to-1 aspect ratio squares. But when we change the cell shape by printing, instead of squares, we're micro-patterning rectangles with 7-to-1 aspect ratios, you can see that we can induce sarcomere alignment. And this is really important in cardiomyocytes or in any muscle cell, because this enables the cells to contract in one direction and produce sort of optimal force generation. And then we talked about at the beginning of lecture this application in tissue engineering. So we can make sort of cardiac microtissues that are aligned onto arrays of lanes. And these are very reproducible. We can create reproducible sizes and promote cell alignment for experiments. So we talked about micro-patterning with PDMS, so microcontact printing of cell adhesion proteins on PDMS. But what if your biomaterial is already adhesive to cells, such as gelatin? So in that case, we can use the same PDMS stamps in a process called micromolding, where we've talked about how gelatin forms a hydrogel overnight at room temperature. And so in this case, a PDMS stamp is placed in contact with that gelatin solution, and it forms a hydrogel while it is in contact with the stamp, such that once it has formed a hydrogel and you peel away the stamp, you're left with these the surface topography that sort of mimics ridges that can similarly align cells. So in A here, we have the gelatin hydrogel without those micromolded topography. That's in A, and you can see that the cells are not aligned with one another. Whereas in B, when cells are cultured on the micromolded surface, they do align with one another. And on the top right here, we show a micromolded gelatin hydrogel that has actually been engraved with these cantilevers, these rectangular cantilevers, such that when the cardiac myocytes or skeletal muscle cells that are seated on the surface contract, they'll actually, the cantilevers will deflect, and their displacement can be used to start to quantify the contractile stress of these cells. Okay, so now we have some more questions on soft lithography and microcontact printing. So photolithography creates patterns in blank, while soft lithography replicates those patterns in blank. Okay, looks like we've hit our threshold. So the majority of you said photolithography creates patterns in silicon wafers, and soft lithography replicates those patterns in PDMS. That is correct. So remember, chrome masks are the masks that are used in photolithography to create patterns on the wafers. Okay, so the next question is Pluronic F127 has a blank center that interfaces with PDMS and blank ends that interface with water or the cell media solution. All right, let's reveal the answer. So most of you said the center was hydrophobic and the ends were hydrophilic. That is correct. So the hydrophobic center will preferentially absorb onto the PDMS surface, which is hydrophobic, and the hydrophilic ends will lift off into the water-based solution. Blank is not naturally adhesive to cells, which can be resolved through blank. So is it gelatin or PDMS that is not naturally adhesive to cells? And do we resolve this through microcontact printing or micromolding? We'll wait for like 3 more of you to respond because that's approximately the number of responses that we've been getting. And then again, if you don't know, just guess. Okay, we'll go ahead and reveal the answer. So the majority of you said PDMS is not naturally adhesive to cells, which can be resolved through microcontact printing. That is correct. So PDMS is not naturally adhesive to cells. Gelatin is. Gelatin is a derivative of collagen, which is an extracellular matrix protein. And so we can pattern cell adhesion proteins onto the surface of PDMS through microcontact printing. Okay, and so in the last segment of class, we'll discuss microfluidic devices. And so microfluidic devices are have small features on the scale of 10 to 100 microns, which is similar to cell size. So this allows us to easily compartmentalize cells, test multiple conditions in parallel if we have multiple chambers or channels on one device. And then we can use really small volumes of media and drugs, et cetera, which allows us to minimize basically the cost of experiments. And then we can also connect these devices to sort of inlet and outlet tubing, which is demonstrated here, and start to automate some things such as media changes and drug dosing, et cetera. And so on the right here is just a schematic of how microfluidic devices are made. We kind of talked about this at the beginning of lecture, but you'll start with your master mold, which contains your channel design. We'll do soft lithography, so we'll pour PDMS onto the master mold, cure it, and then peel off the PDMS replica. And then we can drill inlet holes to access the channel. And then in order to seal this channel, we will activate the surface of PDMS, both of this channel surface and also another PDMS cover slip or glass cover slip. And this will create reactive groups on the surface, which can bond together covalently to form our final microfluidic device. And also in this image, we see a dime to demonstrate the scale of microfluidics. So these are very small features. Okay, so one important characteristic of microfluidic devices is that flow is laminar or smooth flowing. So on the right here, we have a picture of laminar versus turbulent flow. So in laminar flow, molecules will travel sort of parallel to one another, and there will be no or minimal fluid mixing. And so this can be characterized through what's called a Reynolds number, which you might have learned about in previous courses. But it basically just characterizes whether flow is laminar or turbulent. And so this is the equation for Reynolds number. You don't have to know this for this course, but I'm just demonstrating that you can see in the numerator here, diameter of the pipe or the channel is incorporated into the Reynolds number. And since we're working with really small dimensions or small diameter channels, we end up with really low Reynolds numbers. And low Reynolds numbers characterize laminar flow. And so this is depicted here in this figure. So if we introduce 4 differently colored dyes into a microfluidic device and allow them to merge at one channel, you can see that there is no mixing of the differently colored dyes. So they'll flow parallel to one another throughout the channel. And again, this is because we're working with really small dimensions and flow is laminar in microfluidic devices. But if we want to, we can easily generate gradients or introduce turbulence to cause mixing of fluid. And so in this example, we can introduce sharp turns in these like sort of serpentine channels, which force mixing of the 2 fluids at the inlet. And so by introducing sort of a series of these, by starting out with just 2 differently colored dyes, you can end up with 9 different mixtures of these dyes. And so in this way, we can test multiple conditions and gradients of things like chemical factors, drugs, et cetera. Okay, so another interesting application of microfluidic devices is what's called microfluidic valves. So a regular mechanical valve is like what you have on like a hose where you would need to mechanically open and close the valve to block fluid flow. But on microfluidic devices, we can actually make PDMS valves in order to enable or block flow. And so this is pictured here. So in blue, we have a channel where we can apply pressure. In red, we have a PDMS membrane. And then sort of in the transverse direction, we have another channel for fluid flow. And by altering the pressure through the blue channel, we can actually deflect the PDMS membrane to enable flow, or return it to its resting position to block flow. And so this is shown in the video on the right. Yeah, that should work. So we have two valves here that are enabling or inhibiting red or green flow. And you can see that that's controlling what flow enters this bottom chamber. So we're oscillating between green and orange flow. So on the bottom here is another application of these valves. This is called a peristaltic pump. So a peristaltic pump is pictured here. This is how like your small intestine moves its contents. You can also kind of think of it as how you would like eat an otter pop. So you would like pinch and just push in one direction to enable flow in that direction. So in this case of a microfluidic peristaltic pump, we have three channels here where we can apply pressure sequentially to sort of push the fluid in one direction. So we're inhibiting flow one at a time until the fluid is pushed in one direction. And this enables us to work with like really small volumes of media. So we don't need external control over this device. We can just circulate the media that's already in the device. And this is like an exaggerated example of how high throughput microfluidic devices can be. So this particular device, you don't have to understand everything about it. Just note that there are 96 cell culture chambers, which are in blue here. So we can test 96 conditions at once on one device in one experiment. And they have very small volumes, which allows us to save on the cost of cells and media and drugs. And we can sort of customize each of these chambers with their cell seating density, media composition, and even their feeding schedule, because we have these things like peristaltic pumps and inlet and outlet tubings that enable us to control flow. And because we're working with PDMS, which is transparent, cells can be very easily imaged on these chambers. So we can start to look at what the cells look like in response to all of these conditions. Okay, so that concludes sort of the lecture on microfluidic devices. So I do have a question for you on microfluidics. We talked about Reynolds number and how it is related to laminar or turbulent flow. So what is one way to introduce turbulence to fluid flow in microfluidic devices, or to cause mixing of fluids? Sorry, I forgot to read out the options, but you can either increase the diameter of the channel, increase the velocity of fluid flow, alter the channel geometry, or all of the above. All right, so the majority of you said all of the above, which is correct. So here's the equation for Reynolds number. And we talked about how really low Reynolds numbers characterize laminar flow. So making this number bigger would promote turbulent flow. And so in this case, in this equation, we see V is for velocity of fluid. So if we make that larger, Reynolds number increases. D is for the diameter of the pipe. So if that's larger, Reynolds number increases. And then I see some of you selected C, which is the example we gave in class. So that is also a correct answer. And that is to just introduce different geometries that cause mixing or cause fluid flow in sort of various directions rather than just in one direction. Okay, so this is like a summary of what we've gone over so far. So we talked about photolithography and its process and how essentially this is just using UV light to create microscale patterns in our stone, right, lithography, which is photoresist on silicon wafers. Then we talked about how Soft lithography is a technique to replicate those features in PDMS. And then we talked about how those resulting PDMS designs with small features can be used either for microcontact printing to control cell shape or tissue structure, or for microfluidic devices to do these really high throughput screenings of cells. And so the rest of lecture, there are maybe like 3 or 4 more slides left on just applications of microfluidic devices in research. So how are researchers actually using this to answer scientific questions? So in this example, we worked with stem cells, sorry, not we, the authors worked with stem cells that were seeded into various chambers on a microfluidic device and then exposed to osteogenic growth medium. So medium that contains like bone growth factors to promote differentiation into bone cells. And they expose these cells in the various chambers to this, these bone growth factors or this osteogenic medium for various durations of time. And then measured the production of alkaline phosphatase, which is a bone matrix enzyme. And you can see that the longer that these stem cells were stimulated with the osteogenic media, the more bone matrix enzyme they produce. So they're starting to turn into bone cells on the device. And the advantage of a microfluidic device is that they could test all of these conditions in parallel on one device. So another application in research is to actually separate cell components. So in this device pictured here, there's a microfluidic channel with pores that are large enough to enable axons to extend through, but small enough to inhibit the soma, or the cell body of neurons, from passing through. And so in this way, they were able to compartmentalize different regions of a neuron. And this is advantageous because let's say you want to injure the axons and then treat the device with a drug to examine axon regeneration in response to that drug. So now you can easily visualize that since the axons have been sort of isolated from the soma on this device. And this is showing it from the transverse direction. So this is the chamber where cell bodies can fit through, and then axons can sort of make it under this small ledge and extend out towards the rest of the device. Okay, so sort of the last application we'll talk about today is to study circulating tumor cells. So circulating tumor cells, if you look at the schematic, are tumor cells that break away from the primary tumor site. They intravasate or enter the bloodstream and then enter circulation. And then at distant organs or distant sites, they'll extravasate or exit the blood vessels and form sort of secondary tumors or metastases. And so there's interest in collecting CTCs in order to understand more about a person's state of their cancer. And so the issue with collecting CTCs from blood is that they're a very rare cell population. So you can take a blood sample from a cancer patient, which is called a liquid biopsy, in order to isolate their circulating tumor cells. But again, this population is very rare. So with microfluidics, we can start to capture the circulating tumor cells and sort of like filter them out and keep them for downstream assays. So this is an example of that. So here there's a centrifuge tube filled with whole blood, or that liquid biopsy that we talked about. And then blood enters through tubing into this microfluidic device. This microfluidic device contains microposts that are coated with an antibody that binds to circulating tumor cells. So as blood flows through the device, circulating tumor cells will hit these microposts and bond to them because they have antibodies that target CTCs. And so you can sort of pass this entire volume of blood through the microfluidic device. And on the chip, you'll be left with the population of circulating tumor cells. Okay, and so another example of this is a second method of using microfluidics to capture circulating tumor cells, is to use a PDMS device with a herringbone structure, which refers to these ridges. that is similarly coated with CTC-specific antibodies. And so if we look at this figure, with a regular smooth microfluidic channel, we talked about how flow is laminar. So the molecules will sort of travel parallel to one another until they exit the device. But with the herringbone structure, this is another way of using geometry to introduce turbulence or mixing. So flow will be disrupted. And this basically increases the likelihood that CTCs, the circulating tumor cells, will hit the ceiling of this device. And because it is coated with CTC-specific antibodies, those cells will bind and get sort of captured on this device. And so we have a figure here demonstrating sort of quantitatively how effective this is. So in a smooth device, which is shown in green here, the capture efficiency or the capture rate of circulating tumor cells is low. Whereas with this herringbone structure where we've introduced turbulence and caused more interactions between the circulating tumor cells and the herringbone structure, we've captured almost triple the number of CTCs. And so that's the last slide of the lecture today. The learning objectives are listed here for you to use while you're studying. But yeah, so if anyone has any questions, now would be a good time to ask. And here's your assignment deadlines inserted by Dr. Cho. Any questions?
Sorry, so Scratch, 7 days until deadline. It's more like 2 days until deadline. Sorry, I realized that those dates are off. I'm gonna write that in chat again.
All right, I'm going to stop sharing my screen if there are no questions then.
All right. With that said, hey, everyone, let's thank Natalie. Hey, this was her first time. She must have been very nervous. All right. She did a great job. Let's give it up for her. Yeah. With that said, again, make homework 4 is due on Wednesday. Okay. Please submit that before 3:30. And then we have our lab demo 2 on Wednesday. So this is going to be our second and final lab demo, unfortunately, of the semester. But we will try to make it as fun as possible. So hopefully you guys are excited for that. Again, Natalie really put a lot of effort into that to edit the videos and to film it. So, hopefully you guys all appreciate it. And with that said, I want to give you guys, that ends today. So you guys can feel free to stick around if you have any questions. If not, I shall see you guys on Wednesday. Thanks again, Natalie, and have a good one, guys.
Thank you,
Natalie. Thank you.
Thanks, everyone.